So whenever you're ready, go ahead.
Thanks everyone for joining ARM HPC webinar. Today we would like to be able to tell you a little bit more about the various different HPC resources that ARM has to offer to the broader community. Give you a little bit of overview of how to get access to it, what these resources are, and how to get started. So, let's see. So overall, ARM offers lots and lots of data sets, and as these data volumes are increasing, there's increasing demand for large-scale synthesis activities, simulations, as well as machine learning to be conducted on these large-scale data sets. So ARM Data Center runs a number of computational resources, which these resources are co-located with the data that enables use to embed and include all the ARM data sets easily within these large-scale systems. So the goal for today's webinar is to sort of give you a high-level overview of what these HPC resources are, how are we going to get started with getting an allocation on these resources, how to get access to this, and then there's some basics of how to get started. What are the different storage resources available? How are we to manage software on these computational systems? These are all scheduled systems, so type of job queues that we have set up, or the schedulers that you need to be able to use. We'll give you some samples of how to write some basic scripts and how to set up your parallel jobs. And then towards the end, we have a little bit kind of more advanced hands-on session that will try to do a demonstration of developing new parallel applications on these systems, right? And we'll have some examples of using Python and Dask type system types codes include, and as well as some more traditional high-performance computing codes that you can write using C and MPI and other different modes of parallelism. So we'll start with sort of a high-level overview of these systems first, and then I'll do that part, and then my colleague Michael Giansaracusa, he'll get into a little bit more sort of in depth on various of these aspects. We have a large group of attendees, so some of the level of detail that we may be going in we'll keep it at a sort of moderate level. But if you have additional questions, we are happy to answer those. Everything that we're going to talk about is actually available on these links that you have on your screen. These slides have been already added to the second the code repository link that you have available on the screen here. This Zoom session is being recorded, and this recording will be made available. Just a quick sort of housekeeping. We are planning to leave at least a 30-minute window at the end of our today's session for a more interactive Q&A. So if you have detailed questions, please hold them off to the end. If you have questions that arises as we are presenting some of these content, please use the Zoom window to post those questions. One of us will be monitoring these, and if it's a quick answer to it, we'll try to answer you with the answer goes within in the Zoom chat. If not, we'll hold it off and get to it towards the end of the session. And then for any questions that you may have for today's session or HPC resources that ARM offers in general, there's an email address that you can write to to get those questions and queries answered. So getting access, that's the first part of how are you going to get access to these resources. Divided, the steps are slightly different. Slightly different for whether you are a science user or an infrastructure user. And just to sort of qualify, the infrastructure user means you are an ARM staff doing a lot of data processing, and you need those resources for doing these data processing and data generations for as an ARM work. Science user, that's the broader scientific community. You may have an ARM or ASR funded project. You're working with these data sets. You're trying to do some analysis. You would like to have allocation on resources. So the first step is to complete an ARM HPC project request form. Again, I will make these slides available, and those web links are, all the links are hyperlinked on the slide that you can use. It goes through the process of review by ARM management, and once you are approved, ARM Data Center staff will set up a project ID, and you'll be provided that. And that has to be set up at a level of a large project, and you'll have an allocation for X number of CPU hours, X amount of storage resources. And then with every individual user within the project will need to go and request an access as a part of that larger project that has already been approved. You have to use that project ID, and if you don't know it, ARM staff will tell you about what that project ID should be. Then there's the last step. You have to go to OLCF account application forms. All our systems are run by Oak Ridge Leadership Class Computing Facility here at Oak Ridge. And then that's the final step where you will go and create an account, and then you will be able to access these resources. For ARM infrastructure staff, all steps are the same, except the first step is not needed. So you can just skip that. So most of the work is being done as a part of ARM work. You don't have to have a specific project allocation. So, but we'll again, these steps are, last two steps are common for just about everyone. You can be part of multiple projects, and every project requires a separate account application. So you can be participating in different parts of different projects, different communities while working on the same infrastructure. ARM maintains two primary computational resources, and especially these are the ones that we are going to talk about today. Cumulus cluster, which is a very traditional Linux cluster that has 119 nodes with a total of about 16,000 processing cores. So this is the main workhorse that ARM has available for all its users. To complement that, we also offer a Jupyter Hub capability, which is an interactive development environment. And I'll have a little bit more detail that I'll provide you that, but anytime you get access to ARM, you always have access to both of these resources at the same time. We'll talk a little bit more detail about how you can transition your workloads seamlessly between two of these systems that actually give you access to all same storage resources, similar software stack, and everything. So a little bit more details about Cumulus clusters. It actually has three different types of nodes, and those are geared towards various different types of workloads that are being run on this system. So the first is there are a large number of nodes, 112 of nodes that we are calling standard nodes. So these are dual processor. They are two AMD processor and every single node. These are all 64 cores each. So on a node, you have 128 cores available. Each node has 256 gigabit of memory available. High memory nodes, there are only 16 of those, but they are in almost all regard they're exactly the same, except that you have double the memory available. So you have around 512 gigabit of memory available. And then we have a few GPU nodes. And these few GPU nodes, again, they're very similar to the rest of the nodes in terms of their processes. They have a terabyte of RAM available, and they all have 4 NVIDIA 800 GPUs on them. We have queues set up, and we'll talk a little bit more about that in order for you to be able to request the resources that are appropriate for your particular computational workflow. So you can actually, with just a small change in your Slurm script, you can easily ask for the resources that fits your workloads better. On the Jupyter Hub, this is the default configuration that you get if you go and log in on Jupyter Hub. You get about 64 cores in that instance with about 196 gigabit of memory. Storage is about exactly the same. You have same home on both those systems. You have same GPFS storage system on both the systems. All the files that you have access to are going to be available on both sides. So a little bit more about the storage that we have available. And So when you log in, the first thing that you see is your home directory, and we've included those mount points. That's really what those paths will look like. Home directories, every single user has 50 gigabit of home space quota available in their home directory. This file system is backed up. So if you by mistake lost something, it can be recovered. There is a project space created, which is available at /CCS open proj and whatever your project ID is. This is a fairly small area. It's a 50 gigabyte of space available for the entire project. This is a backed up space as well. There's no purging, but this is for common files. So if your project has a certain set of libraries that's getting used by everyone, or some piece of data sets that is getting used by everyone on the project, you can keep it in the project space for long-term storage. These are again typically these libraries that everyone is using, and you don't really want to have to go back and touch on it again. But for most of the workloads, most of the work that you do, you will have access to this fairly large storage on GPFS, which is Global Parallel File System. Our GPFS storage on Cumulus cluster has a capacity of about 4 petabyte. So at a project level across all on infrastructure, we have a large amount of data storage space that's available to us. One thing to note that this file system has to be considered as a scratch working file system only. These are not backed up. So while the system has been absolutely stable and we have not had any issues with data loss on the system, there is no guarantee. So anything, once you have completed, when you're done with your analysis, we recommend that you take the data offline and on your own backup space, or if you're creating a data product that needs to go back to the ARM archive, then you follow the mechanism for data release and then archive it in the ARM archives. There are 3 different mount points available within GPFS file storage. The first one is a scratch space, which is specific to you for that specific project. You have read and write access, and by default, file permissions are closed just for you. So no one else can see the file or can write to it. There's a project shared space available, which is by design has been created for a large a project to work together in. So within all the data sets that are within project shared space has by default a group level read and write permission. So you can actually work in that large area, share data with your team. Everyone can read and write from it. But there can be cases where you want to be able to share data sets beyond your project with other users that are on the system. And for that purpose, you have access to the world shared directories. Any data that's is copied over to world shared directory by default provides a read and write access to your entire project, all your project team, but a read access for the rest of the world, as in the rest of the users on the Cumulus cluster or on the Jupyter Hub. So that's the high level schematic of how different storage areas are available to you on this particular system. They are tiered depending on what the work that you're doing. I would suggest that you keep all your codes in your home directory, especially if they are all fit within 50 gigabit limit. And most of the work that you're going to be doing is going to be on GPFS parallel file system. There is no purging as of now, but you may be asked if your data storage, if the overall storage that you're using is extremely large, you may be contacted by ARM ADC staff and asked to reduce that storage, just so that we have all users so that we have sufficient capacity available to all of our users. For the software management, all the software on the system is managed through this environment module. So a very large collection of softwares are already available on the system. And the screenshot on the right shows you this set of softwares that are available there right now. You will see at the bottom, there are also a number of softwares that we custom build and support for on use cases. So for example, if you are on staff, you are very familiar with ADI. ADI and other packages are maintained by on data center staff and are provided as a module. Similarly, for various different use cases, we have built applications like LBL RTM and Mono RTM, and we make it available through a simple module load. We'll touch upon a little bit more of it when we get into a more interactive hands-on component of our today's session. Job scheduling. Cumulus utilizes a Slurm batch scheduler. There are 8 or so different Slurm queues that has been designed to cater to different needs. So you can actually get resources that you are going to need for that particular job. There are some restrictions on who can access what queues, and that may depend on your project needs. So some of the queue access may be restricted. So this is a quick overview of what these different queues are. The batch all is entire machine. So all 116 16 nodes are part of batch all. Their access to batch all is restricted to only the projects that need to run computational workloads that may actually span the entire system, all of 16,000 cores. There are several different priority long, batch long, batch short, and these are just different queues that are designed to give you access to standard memory node versus a high memory node. They are all designed to let you run extremely long jobs, 120 hours. So that's about 5 days. So you can actually run these on for 5 days. There are several queues set up for debugging, and they are just given a little bit of higher priority, so you can actually get access to those nodes fairly quick. GPU nodes sits in a completely separate queue as well. So if you're working with machine learning codes that are going to utilize GPU, you can send your jobs to a different queue and get access to those GPUs. So at this point, we're going to transition to some hands-on work, that hands-on tutorial session that Michael is going to run.
Okay. There we go. Okay. So as G2 was mentioning earlier, when you apply for an account with ARM and OLCF and get access to the Cumulus cluster, you get access to 2 of the main ways to access the cluster immediately. The first one is directly on your command line. I use a terminal called Secure CRT, but if you're using a Mac, there's many other different ways to get in. In this example, I've logged in with my UCAMS credentials, but if you are an external user, you log in with your XCAMS credentials, and you are put on one of the 2 main login nodes. From these nodes, you can develop code, you can run code, you can get interactive jobs on the compute nodes, and you can submit batch jobs to the compute nodes. I mention this because another convenient way to access the Cumulus cluster is through the Jupyter Hub instance that G2 mentioned. This is at jupyter-open.olcf.ornl.org or .gov, as you can see at the top here. The qualifier with this is that you cannot submit jobs to the compute nodes from the Jupyter Hub instance. there just isn't the connection there at this time to be able to submit those jobs. So while this makes a great development environment, you can write code, you can edit code, you can access the terminal, you're not able to submit jobs directly to the compute nodes from here. So we can go into some other ways to log into it. For instance, in my case, I personally prefer to use VS Code to log into the compute nodes. Many IDEs provide remote execution libraries that allow you to log into remote machines via SSH connection. So you're looking at the same file here that we're looking at here, just in my personal IDE of preference. Okay. That being said, if you use an IDE like VS Code and you access it through an SSH connection, if I pull up a terminal from my IDE, this terminal here at the bottom can submit jobs directly to the compute nodes because this is an SSH connection. This isn't a Jupyter Hub connection. So I personally find this to be much more versatile and much more useful. However, the Jupyter Lab instance is incredibly convenient and very easy to use. So now that you've got access to one of the compute nodes, to our login node on the Cumulus cluster, you're going to want to do a couple things, right? You're going to want to develop code, and you're going to want to get the data to run your code on. We provide a number of data transfer methods to transfer data in and out of the compute cluster from the ARM managed resources. Two resources that we would like to make note of here are ARM Live, which is a web service that we maintain, and the Globus web UI. There is a Globus command line interface as well that we will maybe have time to go into toward the end of this, but I'm going to skip over it, at least for this part. So moving data in and out of the parallel file system on the Cumulus cluster using ARM Live is incredibly easy. It's a REST URL service that allows you to stream a byte stream of data directly from our data archive to the destination directory. In this case, we would be streaming data from data archive into the compute cluster, and it's incredibly easy to use. There is a web UI for this service, which you log into with your ARM credentials. So this, when we were going through the first setup, this is the first step in getting access. You have to make an ARM account. So these are the ARM credentials that you log into this way. This REST URL service allows you to query files that are in our spinning disk storage, and then it also allows you to download them directly. I will mention that while you can query files that are on this REST service, this page, while incredibly convenient, will download these files to your local machine. And that is not what we want for this tutorial. So we're going to skip using the web UI, and we're going to go straight to using one of the two clients that we provide. We provide a shell client and a Python client, depending on your preference. The shell client simply interacts with the UI and downloads a byte stream directly into whatever directory the user is in at the time. The shell client uses the same login credentials that we noticed on the main page there. ARM Live, when you log in, will make it very clear that you are given an access token. Each person gets their own unique access token. However, we've created one for this training session that will disappear in about 2 days. Using those credentials, you can run a bash command and the ARM client that you download to download those files directly. Since this is happening inside our infrastructure, it's seamless to actually get these files. And let's see, I can demo this real quick right now. Let's see. That was it. It's incredibly quick for small amounts of data. So in this example, we made an output directory for our files to go into. We downloaded a list of files here and then sent them all to the output directory. These are the files we just downloaded. Very simple. We also have a Python client, which does basically the same thing. It's pip installable. You can download it by cloning the repository. It uses the same credentials that you get from the other page. It has slightly more functionality, but it's generally the exact same. So that's the first way of getting data into the cluster that we would recommend. This is an example of querying the web service using Python to try and figure out what files may be available to you without having to go to the web UI. The next example, this is an example of using the Python client. As you can see, the syntax is incredibly similar. This one just uses flags for the input parameters rather than them being positional as they are for the shell example. So Globus 5 provides a command line interface that, while incredibly convenient and quite easy to use, requires some setup, and we may not get into it until later in the presentation, but I would like to show you how to use the Globus web service. Globus.org has a login page, just like any other, but when you log in, you can get access to some endpoints. In this case, they're called collections. I have these filtered by ones I've recently used, but let's start with something blank. What we're trying to access here on the other end, the Cumulus side, is the NCCS Open DTN. This one right here. When you open this in the file manager, I'm already logged in, but it will ask you to log in right here with your XCAMs or UCAM credentials that you made when you asked for an OLCF account. This gives you access to the entire file system of the Cumulus cluster. Now, your user may not have access to read write on everything, but anything that your user does have access to will be available here. For instance, this demo is running out of the ATM 125 project in the project shared space. This is managed by all the users of this project. This is my user, and this is the workshop. And this is the data we just downloaded using the ARM Live client. If you want to use Globus to get data from our architecture or our infrastructure, there are a couple different collections that you could access. The main one that I would recommend is the ORNL ARM Data Center Archive. This is a read-only collection that allows you to have access to our data archive, the same file structure that you would using the ARM Live UI. you'll notice that this takes you directly into Data Archive. These are all of our sites. We could go into any of them. And if we have some knowledge about the ARM data stream system, I could go and find the data we just downloaded using the ARM Live client. And of course, there we go.
And Mike,
Yes. What's up, Kyle?
sorry, I just thought I saw something. Never mind.
So now, let's see, could E13, hopefully this won't take as long. But transferring data from here to the other side is as simple as pushing the start button. Having the same directory open on both sides that you want to go to, it's very similar to an FTP client. We can refresh the list. They're already here. If we went back to our notebook, we can actually see in the ARM data folder, these are the files that we downloaded with the Globus UI. These are the ones that we downloaded with the ARM Live web service. You can use the Globus UI to get data off of these machines as well. For instance, my cursor is not working. Let's see. Yeah. I've set up an endpoint on my laptop, which will allow me to move data off of this cluster back onto my local machine as necessary. So we've covered getting data on and off of the machine from the ARM infrastructure and back to your machine if you need. Setting up the Globus CLI is not difficult, and there are step-by-step instructions here. But based on the time we have, I don't think I'm going to go into them at this time. We may have some time at the end if you would like to go over Globus CLI instructions. It's very similar. It has all of the same capabilities to search endpoints, to search files on those endpoints, to set up environment variables. The LS checks files, transfers files from one DTN, one collection to another. The only issue is that it does require a batch flag to do it in parallel. It's a little bit more tedious to set up, but it's not difficult, and there are scripts inside this example repository to facilitate that. So now moving on to programming environments. As Chichu mentioned, there are many modules available to you that either ARM maintains or are installed by the Cumulus administrators. There are compilers, there are execution libraries, interpreters, all sorts of parallel processing libraries that you may need. One thing to note, though, if we do a module avail, we're going to get a large list of libraries. If we do a module avail Python, it'll give us a much smaller list of things. It searches for the pieces that you want. If you load one, that follows you around through your execution environment. If you decide to submit batch scripts or batch jobs, sometimes this can override any manual interpreter or execution parameters you may provide. So it's useful to know that if you load modules, they tend to follow your execution around through the different compute nodes and through the different environments. So you can module load a Python environment. I can say module list. I can see that I have OpenMPI in Python. If I do a which Python, I can see that it is the system managed resource one. This one is one of the ones in the CLI 120 group that the ARM group manages. You can also, if you want to just get rid of everything and start from scratch, you can module purge, which is useful when you want to start over. I would recommend, though, if you are switching from one version of a library to another, say I want to go from Python 3.9 to 3.7, you need to either use the module swap parameter or you need to purge and restart. Because if you just try and load both, there are some complications that arise there. That's the swap parameter right down here. Swap's a currently loaded module for an unloaded. I personally find it easier just to purge and restart most of the time. If when you log in, you do not have access or you do not see the same list of modules that I do, I recommend adding this module path environment variable to your either bash RC or bash profile, and then either reloading your terminal or sourcing those two files, which will make these libraries available to you. So that covers getting software on there. You can use Conda, Mamba, or any other package manager that's already on there to load up and maintain your own virtual environments. I personally do that for Python environments. And there are some scripts in this repository to facilitate doing that as well. I can go over maybe some of those demonstrations at the end also. We're going to move into using Slurm on Cumulus. So Slurm is the job scheduler that allows users to interact with the compute nodes on the cluster. When you log into Cumulus, you're initially put onto one of the login nodes, and users do not have direct access to any of the compute nodes except through Slurm. In Slurm, the cluster has been divided up into several different partitions. In some schedulers, this is called different queues. You may not have access to all the same ones that I do here, but if you type sinfo on your terminal, you will get a list of some of the information that will help you understand the cluster you're logged into. Another command that is very useful after you've started submitting jobs is the sq command. I think we have purged the queue recently, so we may not see anything in it at the moment. Oh no, there are still some in there. So this gives you access to see what is running on the cluster right now. This can get a little confusing if you are interested in just your own jobs. In that case, sq-u and your user will give you just the jobs you have submitted. In this case, it's me. I have submitted none at this moment, so you see none in the list. Those commands are listed here as well. You can list running jobs, pending jobs. Pending jobs have not been allocated resources yet and are still waiting. Listing accounts is done by doing this. If you don't know which accounts are available on the system, or you would like to request access to another one, you can always contact us here at ARM Support, Cluster Support. But you can see the list of accounts that you have access to by using the Account Manager. Moving on, these are some other commands you can use to show and monitor the jobs that are already running. They will generally only come in handy when you're trying to debug jobs. nodes. I've left them here for reference for people who are interested in debugging their jobs later. One thing that will become handy though is that sometimes while you're running jobs, you will have workers that get stale or become zombie processes, and it is helpful to be able to cancel them all out. You can cancel all the jobs that your user has submitted. You can cancel just pending jobs, or you can cancel specific jobs using the job name. Holding, releasing, and re-queuing, I have not found to be super helpful, but others who work here, I have seen use it, and so I left it here as well. The srun command is the only way that a user will get direct access to one of the compute nodes. Running srun on the terminal will get you logged into the actual compute nodes. Don't know if I will be able to right now, given that. Oh, there we go. That was fast. So my host went from Cirrus login to Cirrus 14. This is one of the specific compute nodes that's available while you're running your jobs. And so now, while I'm on this, I can run code, submit different kinds of parallel execution code, and see the terminal output directly. This is, I'm on a compute node now. In production mode, when you're doing this with large, long-running jobs, you probably don't want to use srun, but it can be helpful while debugging jobs to be able to use srun to get directly into the compute nodes. If I type exit, I am back on the login node, and this is where you would run batch jobs. Some of the output from when you log into compute node. Okay, so running batch jobs. Batch jobs allow you to request and allocate resources for long-running jobs that are going to be using any amount of the resources of the compute cluster. We have some examples here of how you would set up and run one of these jobs. G2 mentioned earlier the structure of this. So if you do sbatch, and then you pass it the name of this specific file, I'm going to allocate one node on the ATM 124 project. This is the wall time, the running time for this job. If it hits this time, it will stop. There is another set to this. So it starts with days, dash hours, minutes, seconds. So if you need your job to run for several days, you would specify it this way. Now, I don't like to log into the cluster every time I need to check on a job, and so you can have it email you. Set up your email. Do I want to be notified at the begin, end, if it fails, if it gets requeued, or all of them? Normally, you would not run this with all as a specific parameter in addition to all of these, but I put them here for reference. And then partition is the name of the queue that you're submitting to. G2 earlier mentioned that the different queues have different resource allocations and availabilities. All will give you access to any of the nodes, and we'll try and put you on the ones that suit your needs of the script that you're running. In this case, we've module loaded one of the Pythons. This actually wouldn't happen. This was an example of where I have my own Python environment here. If I try and activate my own Python environment, what will happen is this one will end up overriding it and following it. So this ends up being whatever module I loaded and not the one that I tried to source. It's just an example of how that can get confusing if you're doing a personally managed environment and also using a module load. So now we're going to go into something that's a little bit more useful for long-running very parallel jobs. It's called job arrays. So a job array allows you to run an SBatch job with a list of environment variables that each executing process gets. So in this case, when you run an SBatch with an array of say 2, 4, 6, you've got 3 jobs, and each one will get an environment variable called job array index value, or slurm array task ID. There are many other environment variables that get passed in when you run a job array, but this is the one you want to check, because each time your script gets executed, it will get a different task ID for each running process. You can use that task ID to map across some scalable value that you want to parallelize your code on. It could be a dimension, it could be a day, a list of execution days, a list of files, anything that you want to scale across. Let's say I have a list of files. I have 100 files. I could say SBatch array 1 through 100, and then I could map each one of those numbers to one of the files in my array and execute that job on 100 different nodes, and they would all happen simultaneously. It allows you to create separate output files, do a lot of really clever things by just mapping that job slurm array task ID to a different value. This is an example of what a Slurm job array would look like. So in this case, I've given my job a name also. If I went and did an SQ, it would show me the jobs, but also the name of those jobs. If I gave it something useful, then I could monitor my job based on that name. In this case, instead of giving it specific numbers, like 2, 4, 6, like we saw back here, or a list, I've given it a range, 1 through 20. So this will give each task ID the numbers 1 through 20. I've said that the wall time is an hour. I want 1 task per node. I'm giving each task 1 GB of memory. I have each file outputting a different output file. I'm using that project. This is kind of some of the stuff we went through already, and I'm using a different queue in this case. I'm using the priority long queue. And now this is doing an srun and just doing a simple bash command, but this will give us an example of what this would do. So let's head back over here, give this a try. Make sure we're in the same place. I'm not. I have to go to my project, TM125, project shared, me, this workshop. So now the one we're looking for is this one. But I'm actually not going to do this here. I'm going to do this in a runs directory because I'm going to get a bunch of output files. I want to kind of keep them a little segregated. So SBatch backup directory .slurm. So I've submitted a job. And there they are. Those are the jobs I just submitted, running on a selection of different nodes. When we did the srun, we logged into a specific one. We were on one with a much lower number. I think the lower 50 are the ones you usually get into for the srun, which are interactive. But if we start looking in the directory we're in, we're seeing output files already. We can cat any of these output files. Let's say I want 1.0. So in this batch command, we just echoed that we started, echoed the date, we slipped for the same number of seconds as our task ID. So each one gets a task ID 1 through 20. So each job would sleep for a different amount of time. If we had watched this interactively, we would see them complete at different times. And then they echo their number. So if we look in here, we can see this one started. It's task ID 1, it waited for 1 second, and then it finished. This is an example of how you can use that environment variable to map across a list of things you want to scale across. The Slurm array is a very useful tool to be able to parallelize your jobs relatively easily. Another example of how to parallelize your jobs relatively easy is using a Python library called Dask. I'm going to go over a very simple example. Dask can get very complicated very quickly, but I want to talk about Dask to highlight one thing. Dask data frames share the same basic API structure, the same basic methods and interactions as Xarray, Pandas, and NumPy arrays. So Dask arrays are interchangeable with NumPy arrays, and Dask data frames are interchangeable with Pandas data frames. Now, Xarray data frames are they have a lot more functionality than those other two, and so not everything maps exactly, but there is a lot of really good connections, and the same people who maintain both Dask and Xarray communicate very frequently. In this code, we've just opened up, we've loaded Dask and Xarray. LogGuru is just a logging library. We've created some environment variables, some global variables in our code, started up a logger, and this is an example of how you would open a multi-file data set. When you're using Dask, it is generally a good idea, unless you have very specific slicing parameters that you want to follow, to allow Dask to do some of its own partitioning. So in this case, we're taking every input file that we staged and loading them up all into a single data frame. The issue with Dask, though, is that it creates a computational graph. Right here, the code hasn't done anything. It's just said, when you hit the compute button, I'm going to do all of these parts in order. So I've taken this multi-file data set, I've created partitions out of it. So I've used Xarray to open a bunch of files. I've turned them into a Pandas data set. I've turned that Pandas data set into a Dask data frame. And then I've just printed it out. Now you can see there's no values here. It looks like it's an empty data frame. And it's because Dask hasn't done anything with this yet. It hasn't actually loaded it. Dask is very useful because you can hold items in your code, data frames, data arrays, large graphs that are too big to fit in your memory, because Dask manages those in a Scratch hard disk space, and then allows for the partitioning and loading and executing across that in this computational graph that it creates. In this case, I've picked a start and end time that are not exactly the same start and end time as the files I've loaded. I've sliced that data frame across that start and end time, and then I've called compute. When you call compute, this is when Dask goes and executes that computational graph. It will partition it based on whatever you asked it to. In some cases, you can use it, let it do an auto partition, or you can partition it across different dimensions, say time, lat, long, any of the dimension variables in your file. And then in this case, I've just printed one of the specific parameters that I wanted to grab out of it to show you that now this same data frame that looks empty up here actually has data in it, because Dask finally went and evaluated that computational graph. We're getting close to the end of the hour here, and There are many more things that we could talk about, but I wanted to take a break to see if we have any questions, anything we would specifically like to cover at this time. Plus, I need a sip of water.
If you have a question, you're welcome to unmute yourself and ask. Or you can leave it in the chat.
So all of these files too are available in the repository that G2 mentioned at the beginning. There's significantly more content here than we're going through today. We have demos using Xarray, demos using the NetCDF library. This here is the notebook that we're going over today. There is a single line script to just, so you don't have to remember how to get an interactive session. I just run this. I don't even remember the actual parameters most of the time. I just go back and run this one, which I find very useful. Let's see, what else is there in here? There's an example of how we parallelized an ingest, our AOS SP2 ingest. This is the Slurm script that allocates the resources, activates one of our ARM managed libraries, sets some environment variables, calls Python, and calls a processing Python function. This is the Python function that it calls. Oh, wait. Okay, so in this one, it's using the task job queue and the Slurm cluster, along with the subprocess module to spawn a list of jobs across a function. It's mapping this function across a list of files. In this case, our ingests create one output file for each input file, so it makes sense. It's a logical unit to scale across. We don't print anything to the console here because the output files are our output. In this case, even though we're using the task job queue Slurm cluster interpreter, right? This is a method, a plugin for Dask that allows it to communicate with the Slurm scheduler. It's helpful to run Dask jobs that use that in an SBatch to pre-allocate the resources. If you try and run it without pre-allocating the resources, sometimes Dask will get ahead of itself and will have a segmentation fault because it won't have the resources allocated at the time that it runs. And so it helps to wrap it in something like this. So that's an example of why, say, this NetCDF example, well, it does use the Slurm cluster to allocate resources. We wrapped the whole thing in a Slurm job to pre-allocate. It helps the Dask Slurm scheduler work a little bit more seamless. So those are a couple examples of how you would do the Dask Slurm cluster object. And then in the same way that the ingest maps a function across a list of files, this is the function that you would run. And you would call your client compute on the computational graph that you create here. This just maps the files across that function that I create. When you call client compute, then it goes ahead and executes the whole graph. In this case, we gather the results back and then print them to the console because we're not printing output files for this one. But this is an example of how you would do it in Dask. You would still want to wrap this in an SBatch file. So I'm going to fall back to our demo notebook now. Oh, I thought I heard something. just going to press that out. Talk until I'm blue in the face, but if people have specific questions, I'm happy to go over those. But here, I'll run through the end of this example. And so Dask data frames can hold data that's larger than would normally fit in memory. And one of the benefits of using Dask is that you can actually develop this code with a tiny file on your local machine. And then for the most part, you can copy the code directly to the Slurm or to the Cumulus cluster, wrap it in an SBatch script, and it should run the same way. It should run exactly the same. It should just scale across a larger number of nodes, depending on how you've configured the resource allocation. And so here are some examples, things you can do with Dask. Created heat maps of relative humidity versus temperature, scatter plots. I mean, this is all relatively easy to do. You can take these, and when you're done, you can save your plots rather than show them. Show just prints it to the console, but if you're running it on the Cumulus cluster, it wouldn't show anywhere unless you're running an interactive job, but it still wouldn't show it. So you would want to save your scatter plots. Then you can use the Globus UI like I showed right here. This is my laptop. This is the Cumulus cluster. I could just take those plots that I created and pop them right back over. Go to here, go to the folder you want, wherever your output files are. Let's say you have them in the runs directory. These were the Dask job arrays that we had earlier. I could take these and just hit start, and they'll queue the transfer to send them over to my local machine. It's incredibly convenient. So scatter plots, wind rows plots, tons of examples of how you can utilize Dask and the built-in scikit-learn modules. Scikit-learn was developed in conjunction with Dask and some of the other parallel libraries, and it maps very well to parallel execution. So you can also slice arrays. This is an example of pressure over time. In this case, this is a good example of how we can load many files at once. This is multiple days worth of files that I loaded with the load MF data set. Just give it a wildcard flag, and now you've loaded an entire week, month, years worth of data into a single data frame that you can then map a function or some computation across the entire data set. I know how Curia likes histogram plots, so I put one in there just for you. But yeah, so there's tons of stuff you can do. If you have any more specific questions, I'm happy to answer them. That's about as much content as I was prepared to present, but I can keep going.
Pause here and see if we have questions. So if you have questions about particular examples that Michael talked through, or in general questions about getting access to the resources, or what's available, what's not available, we're happy to take them.
I will mention one thing. We did say that we would provide an MPI example. I didn't have time to finish that one before this, so I will be uploading it to the repository. If you just keep your eye on it and clone it, you should be able to clone it directly from our infrastructure into the Cumulus area. We should be adding some examples where we use GCC to compile and build our own packages so that you can do that as well. And then we're going to provide some examples that use MPI to scale jobs in that way, rather than using the Slurm task array, or using Task or Python or any of the other methods that we talked about.
Any questions? Feel free to unmute yourself and yeah, you're here to answer.
I could start off with a silly anecdote. Today is National String Cheese Day. So if you're feeling silly, you can go eat a string cheese. They happen to have a couple extras. My daughter's lunch had one in it today, so.
There is a question.
I don't see the question.
So-
Let's see. There you go. Okay. So the question is, if you want a specific module to be loaded or installed, how does that work? Can I ask a follow-up? Well, I'll just assume both answers. So if it's a Python module, you can download and install Conda, Python, Virtual Env, PipX, Mamba, any of the package managers that you see fit, and build it that way. Like for instance, when I'm over here, do I have Mamba? Let's see. Mamba Forge. And list. So you can install Mamba and then you can activate time. Oh, back. So there we go. 11. I haven't configured it. So I wanted to start this one with nothing. So I haven't initialized the Mamba repository, but you can download a virtual environment manager and you can pip install, Mamba install, Conda install, whatever you want. Build packages directly in. You can install them directly from Git. You can do a pip, Python-m pip install directly from a GitLab repository, or you can build and run your own packages in that way. Like I mentioned, we haven't got a demo of how to build and run your own packages or build and maintain your own packages with one of the compilers that we provide, but the module avail will show you some of the compilers that we have. There's GCC, there's a Go compiler, there's several that you might want. So you can build and compile your own packages directly on the machine, either in the command line or using an IDE of your choice. Like in my case, I personally would use VS Code for everything if I could. So I use this primarily because it has extension support, it has linting, and all sorts of really useful features that go with it. You can even build images, Docker images directly on it and try and import them into Singularity, but it gets a little bit confusing, and we may go over an example like that in the future as we add more content to the repository. You can also always just contact us. You can contact ARM at Cluster Support. We'd be happy to work with you to either help you build it or figure out a way that we can get you achieved. Hope that answered your question. I wish we had a little bit more content to show you about how to build and run your own packages, but that was not available at this time.
Okay. If there are no further questions, then we'll close the session for the day. We'll make all the content, all the slides, everything that available online. We'll post it on the ARM website. These recordings will be posted on website. And if you have any further questions, send us an email at clustersupport@arm.gov, and we'll do our best to answer them. And thanks for joining the session today.
Thank you for the communication team for setting this up and for providing support for it. We really appreciate all your hard work.
Thank you, guys.
Thank you all.